Hey, what's up, guys? This is Chung here. So today, let's revisit this problem 399, evaluate division. So yesterday we talked about this problem by utilizing like a graph and DFS search solutions approach, or you can call it. Basically, we just built like a graph with an edge from this A to B and with a weight of this. And then later on, we just for each of the queries here, we just do a search uh, with this the first element item is the start, and the last one is the end. And we just do a search. And while we're doing the search, we also basically update our current values. So that's the first approach. So now for those for someone who is interested in like another solutions, which is called uh, Floyd Floyd uh, Warshall algorithm. I'm gonna so this time we're gonna use this Floyd-Warshall algorithm to solve this problem. So for those who don't know what is the Floyd-Warshall algorithm, it's an algorithm to calculate the shortest path between all the nodes in a graph. So basically, if we have a node here, if we have a few nodes here, okay, it doesn't really matter, okay, different nodes. And each node has like a different path, right? I mean, something like this. And each edge has like a value here, 1, 2, 3, 6, 9, 7, 9, 10. So here, it's going to be it's a weight on the edge here, okay? So, I mean, I think most of you have already must be familiar with the Dijkstra algorithm, right? So basically, the Dijkstra algorithm or the what is that like Bellman-Fordman? So those two algorithms are only designed to calculate the shortest distance or the shortest path between one set between one like between the starting point and the specific ending point. Okay, and the ending point. That's basically you have a fixed starting point and a fixed ending point, and then you use the Dijkstra to calculate that. But the Floyd-Warshall algorithm is designed to calculate the shortest distance among all the pairs. And this algorithm is especially very useful to in the social network, to calculate the basically for each of the persons, what are the shortest distance between each of the person. And the way this algorithm works is that because it's let's say from the I to J, if there's a I to J, okay, and if there's an I to J here, so the way this one is, I think it's utilizing the dynamic programming concept here. So basically for each I and J, let's say there's a start and the end point. Basically we're trying to find all the possible uh intermediate path, which is the I to K and the K to J. Okay. If we find the intermediate here, basically we try all the intermediate path from I to J, and we're trying to see if this one plus this one is smaller than the current I to J, and then we know, okay, we find a shorter path. Basically, we're doing this by looping through all the possible combinations of I to J, and also for each of the combinations I to J, we try all the possible uh, K case node. Okay, basically, if let's say if the V is the V is the number of the node, the number of nodes. So we're gonna have like for 1, to V. Okay, so basically this is for K for K for K 1 to V, and then for I 1 to V, and then here we have a for J 1 to V. Okay, if there's a matrix, right? If the matrix, what is that? Uh, I K plus matrix of the K to J is smaller than the M of the I to J. Okay, then we just assign this M to J. We just update this M J with this one here. Okay, right? And as you guys can see, so basically that's the basic solutions. Basically, is for for this Floyd-Warshall algorithm, the core piece is just like 3 nested for loops. Basically, for the for each of the I combinations. So we're also including the I to I, but it doesn't really matter. So basically, for each of the I and J pair combinations, we try all the possible intermediate path. Okay, if this intermediate path of that can give us a smaller numbers, right? And then we just we'll just update that one to basically after this for loop we have the smallest length from I to J. So the basically this thing works because if we have a shortest path for I to K, and we have a shortest path from K to J, and then the total of those two will basically will give us the shortest path for I to J. And we're doing this for all the combinations of I to J. Cool. Yep. So that's basically how this Floyd like Warshall algorithm works. And in terms when it comes down to our problem, basically, the V is what? The V is the number of the of these letters here. Okay. And the values, right? The values for like for A to B is K. Okay. And of course, the values for B to A is the one divided by K. Okay. And but for our problem, since it says there's no contradiction here, and we don't have to worry, we don't have to compare this value here. So the contradiction means what? The contradiction means from I to J, there are like more than one ways to get here. That's why we need to in the original Floyd-Warshall algorithm, we have to compare. We have to basically find the shortest path among all the passes from I to J. Okay, that's why we need to do a if here and we update. But in our case, since there's no contradiction, it means that from this I to J, there's only one path to get to the I to J. So all we need to do is that we just utilizing we will just utilize this like the structure here, but instead of doing this one, we just multiply everything. We multiply all these things. We multiply all the b all the intermediate path together to get our final one, because that's how we calculate this our queries here. Because for A and C, so for A and C, what does this one do? This one means that for M A to B times M B to C, right? That's how we get the A and C. And the thing, we just pre-calculated all the possible things here, and we'll just in the end we'll have like a matrix that can give us all the results from any of the combinations here. Okay, cool. So enough talk. Let's code these things up here. All right. So for the to be able to do this, since we're going to loop through the all the nodes here, right? So the nodes is we're using like the index here, okay? But we are having like a string here. So for in my case, I prefer to convert each of the strings here into its index, so that later on we can just simply use the integer to loop through each of the nodes here. I mean, of course, you can still use the dictionary, and later on you just loop through the keys of the dictionaries, but either way is fine, right? So in that case, you don't have to convert into index. But in my case, I still prefer like an index. So uh, let's see. I'm going to first create the indexes dictionary, and then I'm going to convert those things into an index here. So the way I'm converting it, I'm just do a for a and b in equations. Okay, here basically if a is not in the indexes, and I just indexes dot a equals to index, and after that, we just increase it by 1. Same thing for B, right? If B not in indexes, we do indexes B goes to index, and then we do also do a index plus 1. So now we have indexes for each of the letters here, and then so now the total number is n here, right? So the number is the length of the indexes here. That's basically this is the vertices of the entire graph. So now we just need a matrix here. So the matrix, and let me see. At the beginning, right? So I mean, not all the nodes on the matrix is valid, right? I mean, we can set that value to system max, or we can simply just set everything to none at the beginning. Okay. N for n in range n. Okay. So now let's populate. We need to pre-populate this graph first, okay? So that we can loop through that, because we need to initialize this 2D matrix with this equation here. So basically for I in the A and B, okay? In enumerate this equations here, and cool. So what do we have? We have I'm going to have index 1 equals index is A here. Okay, and index 2 equals to index is B. And I'm going to have a value here. So the value is the values of I. So basically the M of I1 to I2 will equal to V. And same thing for the reverse for the reverse direction. Okay. And we can also set these things here. So basically I1 and I1 equal to 1, and M I2 is equal to 1, right? So this is also obvious, right? Because for this letter itself, I mean, right? For the letters divided by itself, but that's basically the AA case here. We set these things to 1. Okay. Now we have an answer here, right? So we have an answer here, and now the it's the sorry, not the answer. So now we have to basically to calculate the shortest path among each of these combinations of our index of our the each of the nodes here. Basically for k in range n, right? And then for I in range n, and then for j in range n. Okay. So like I said, since there's no contradiction path from I to j, we can simply do this. ij uh, equals to m I to k times m k to j. Okay. Uh, yeah, but I think we have to check if m I k is a valid, right? Basically, if and m k j. Yeah, because not everything, right? Since we're like checking all the possibilities and we initialize this matrix 2D matrix with like this none here, right? I mean, not all the combinations is provided here. Basically, our equations doesn't include all the combinations, right? From each of the node here. That's why I'm going to check basically if both of this like the two parts are a valid one, then I update this. Okay. So now we have everything in here. Okay, which everything we know for this query here. So now we just need to populate this answer here, right? So basically the for A and B in the queries, and of uh, so the first thing is if A not in indexes or B not in indexes, okay, we simply do a append -1. Okay, that's the first case. Then second one is else what? Else, which do a I1 equals to the indexes A and I2 equals to the indexes of B here. Now we have those two indices. We simply check. Okay, simply check if this M I1 and I2 has a value, right? If it has a value, then that's our answer. Okay, I1 and I2. Else, same thing. Else it's just another -1 here. Okay, and here in the end we simply return the answer. Okay, cool. Try to run this. Line 3, what? Oh, come on. Yeah. All right, so this one, let's try to run the code. Yeah, cool. As you guys can see, this one's pretty fast, you know. So why is that? Because okay, so the time complexity for this problem, you know, I think it's pretty straightforward, right? Basically, it's the O of the n cube. So why is that? Because it's this one. It's the we have here. So we have an n here, right? So that's the main part of the time complexity, which is n of the O of the n cube here. And the space complexity is gonna be the O of n square, right? And also the so what is this n here? So the n is the number of this the number of our nodes here, and the nodes is since our equation is within the length of 20, and each of the equation can have up to 2 nodes here. So in total, the nodes will be like 40. Okay, total in 40, and so basically the time complexity is the cube of 40, so which is pretty fast. Yeah, I mean, yeah, basically that's the Floyd-Warshall algorithm. You know, I haven't seen this algorithm a lot during like the interview problem, but but I think it's a good technique to know, right? Especially for this like especially with the templates not that hard. Basically, it's just trying to split the the path from I to J into two parts, and then we're trying to find out the smallest one from those two parts. But since in our case, since there's no contradictions here, and we can simply assuming, right? We can simply assuming the the MIK and MJK is one of our valid paths, because for those paths that are not valid, they have already been filtered out by using this if statement here. Okay. Yeah, I think that's it for this problem. Thank you so much for watching the videos, guys. Stay tuned. See you guys soon. Bye bye.